Test. Test.
Yeah, that's how it works, sir.
Yeah, so we've heard a couple talks this morning about the potential dangers of artificial general intelligence and the potential of an open source and generally open development model to some extent mitigate these risks. I'm going to take a somewhat different direction now and talk about a project aimed at actually creating artificial general intelligence, creating machines that can think as well as people and ultimately, hopefully, much better than us. Joel, who spoke a little while ago, is part of this project, as is Genoa, who will speak after me. The project is called OpenCog, the open because it's an open source project, and it's a project that falls under the general category of AGI, or Artificial General Intelligence. And this is a term that I introduced to the world a few years ago, maybe 05 or 06. We were editing a book, myself and my friend and colleague Pei Wang. We were editing a book on approaches to making thinking machines, and we were struggling for a title. My original title was Real AI, and we finally decided that was a bit too edgy to say that we're doing real AI and everyone else is doing bogus AI, although that is kind of what we thought. So I emailed a bunch of friends, well, come up with a better title that's less obviously egomaniacal and offensive. And Shane Legg, who is another AGI researcher who I'd worked with in the late 90s, another Kiwi like Joel, as it happens. Shane Legg said, well, what about artificial general intelligence? General intelligence having a well-recognized meaning in the psychology field. And we thought that sounded all right. We titled the book Artificial General Intelligence. And the term has spread somewhat now. I mean, we have AGI conferences every year for the last few years. The last one was at Google's headquarters in Mountain View, California in August. And the next one will be at Oxford University at the Future of Humanity Institute, late 2012. And 2013, we're going to bring the AGI series back to China, actually not back to China, we're going to bring the AGI conference series to China for the first time. It's going to be in Beijing together with the AGI, International AGI Conference. When it comes down to it, I don't like the term AI that much, in the sense that we're looking at building minds that are going to be autonomous minds. But artificial is about being an artifice, a tool for someone else. And we're not really trying to build tools. Synthetic intelligence, or synthetic general intelligence, might really be a better term. But AGI seems to have stuck, and it seems to resonate somewhat because the term AI is well known. What we mean by it, broadly speaking, is a system whose intelligence is not restricted to any particular narrow class of tasks or problems, but that is able to confront a new problem area, a new set of problems that it never heard of before, never thought of before, that its creators didn't even know about, and figure out what's going on. The ability to generalize to new tasks and new domains. And this ability is not going to be unlimited for any finite system. To make a system that truly, totally general intelligence, you need infinitely powerful computers. Then you'd make a superhuman God mind that could solve any problem perfectly. I don't know if that's possible. It's not really what we're working on. But clearly human beings have a much more general kind of intelligence than, for example, a rock or a mouse or any AI program that we have created so far. And that's what we're aiming at, a level of generality of intelligence comparable to humans, and then going beyond humans. There's a lot of different approaches to creating advanced AGI. You can try to do work inspired by how the brain works. You can try to build an artificial life system and evolve a population of AIs that need to compete with each other to survive and get smarter and smarter. You can use the mathematics of general intelligence to try to derive equations for how an intelligent mind should work, which Marcus Hutter and some others are trying to do, particularly in the German AI community. You can look at AGIs emerging from the global brain of many people interacting on the internet through various social networking tools. You can use a computer science-based approach where you try to implement a bunch of smart algorithms and connect them together, which is closer to my approach. So OpenCog, it's an integrative system. There's some parts of it that are more biologically inspired than others. On the whole, it's more computer science-based than anything else. I don't think OpenCog is the only approach to making an advanced AGI system. I think there's going to be many, many, many approaches that could work. I just think OpenCog is one approach that could work. A rough analogy is flying machines. There's not one way to make a flying machine. You got airplanes, helicopters, balloons, spaceships. I mean, when I'm asleep at night, I can even flap my arms really fast and fly. But I haven't gotten it to work in working life yet. There's a lot of ways to make flying machines. There's probably a lot of ways to make thinking machines. But if you want to implement something, to build something in reality, you have to make some concrete decisions. And we've done that in crafting OpenCog. One important question, once you start looking at a computer science-based approach, do you make a single core algorithm and just go with that? Say a logical reasoning engine, or an evolutionary learning algorithm, a certain neural net architecture? Or do you try to make multiple processes, which are very simple, have them interact together and have a kind of self-organizing emergence of intelligence? Or do you get a number of complex cognitive processes and try to make them all interact together in a certain way? And this third approach is when we take an OpenCog, which is both the best and the worst, I think, because it's the most complicated, because you have a bunch of really complicated things, and you have to deal with the interaction of all these really complicated things. On the other hand, you don't need one algorithm to be that great that the one algorithm can do everything. And you don't have to rely on really complex, hard-to-tune, self-organizing interactions to do everything. You then have a question of where to focus. Do you focus on the cognitive architecture? Sort of what are the parts of the mind? How does information flow between the parts of the mind? Or do you focus on the learning algorithm, the ability of some algorithm to recognize patterns in itself and in the world? Or do you have to focus on both and on how they work together? And in the AI field, good old-fashioned AI approaches such as SOAR or ACT-R, for example, are focused on the architecture, whereas the machine learning community, which has emerged more in the last decade or two, is focused more on the learning algorithm, with the idea being if you can learn and recognize patterns, you can kind of slap that into any cognitive architecture and it will be smart. And we've tried to pay careful attention to both of these in OpenCog, again, making things as difficult for ourselves as possible, because we really like hard work. Knowledge representation. So do you represent knowledge explicitly, like in logic formulas, or in language, or in nodes and links with particular semantics? Or do you focus on emergence of knowledge representation, having the system be able to learn to represent knowledge in new ways based on its own experience? And again, we're very greedy and try to have it both ways. So that can't really be seen on that. Well, it's too small. Ah, it's kind of, it's too small, but you can kind of see it. All right, so this is an attempt to graphically depict some of this stuff in OpenCog, which I cannot see. It doesn't work perfectly on a projector, but it's all right. So we have something called the atom space here, which is a collection of, can I click forward and backward? No, that's just a pointer. I'm too stupid to use this pointer. Yeah. We have a knowledge repository called the atom space, which has a collection of nodes and links of different types. There's nodes and links representing declarative knowledge, like facts and beliefs. Nodes and links representing associations, which things have been associated in the system's history. Nodes and links representing procedures for how the system can do things, like take a step forward or say a word. Nodes and links representing the goals and feelings of the system. And then there's a bunch of cognitive processes that act on this space of nodes and links. And there's probabilistic reasoning. I can't even do that. Okay. Probabilistic reasoning, which works on declarative knowledge. There's procedure learning, which is done by a kind of evolutionary programming. There's special processes for encoding and recalling episodic knowledge. There's processes for recognizing kind of holistic patterns in the atom space, which we call maps. There's processes for dealing with space and time and patterns there. And then there's a bunch of lower level stuff, like hierarchies for perceiving information from the world, for enacting in the world, for recognizing patterns in language that's said to the system. And all these parts need to work together, which is the complicated part. So here, this shows some of the arrows by which things that come up out of perception and go down into action. The perception and action hierarchies all have to interact with the nodes and links in the knowledge base. The cognitive processes also act in certain ways on all the nodes and links in the knowledge base. And then there are certain key processes that happen throughout the knowledge base, such as new atoms can be formed to represent new ideas. Atoms that are not useful can be forgotten. And when they're forgotten, they can either be saved to disk or they can just be kicked out and thrown into the ether. Everything in the system's memory has a short and long-term importance value. The short-term importance tells how much attention it gets from these cognitive processes. The long-term importance tells whether it gets kicked out of memory. And much of the system runs on probabilistic reasoning, so the nodes and links in the knowledge base have a truth value, which is based on probability theory. So there's a lot going on here, and it would take a long talk to explain all the details of all the different cognitive processes. One of the key principles is to combine explicit and implicit knowledge representation. So explicit knowledge representation is like logical knowledge, like a cat is an animal, or if I hit myself on the head, it kind of hurts. Implicit knowledge representation is more distributed, self-organizing knowledge, like in a neural network. So there's no one node or link that represents it, but it could be a whole pattern of nodes and links. So this illustrates some explicit knowledge about cats. So you actually have a node for the word cat, a node for the concept cat. The cat concept node connect to the feline concept node, and it's all very explicit. It's the kind of thing you would learn from hearing people talk about stuff in language. On the other hand, you can also have implicit knowledge, whereby, say, that the collection of nodes and links at the top represents a chicken. The connection of nodes and links at the bottom represents food. And most of the nodes there have no names, because they're not English things. They're just nodes that the system formed to cluster together certain patterns in its mind space. And so then you have bundles of links between bundles of nodes, most of which don't have names, but they're just things the system formed on its own. And this is a kind of implicit knowledge rather than explicit knowledge. And you need both of these to work together. Among the many learning processes on that big confusing chart I showed before, there's two of the most important ones are PLN, the probabilistic logic network system, which was largely built by two dudes from New Zealand in the audience, Joel and then Jared, who's back up there, which looks at the nodes and links in the system and tries to build new nodes and links based on them that probabilistically thinks will be useful for the system achieving its goals. And then Moses, which is a system for basically learning programs based on the system's experience. So if the system, let's say, needed to know how to throw something up in the air and catch it again, because it was controlling a virtual agent or a robot, it might use PLN to logically reason about how to do that, or it might use Moses to evolve a little program in its mind telling you how to do that. And which of these algorithms is best for doing that would depend on the particulars of the situation. One of the key ideas here is what's called cognitive synergy, wherein all these different modes of learning, the logic engine goes with declarative knowledge, and Moses procedural learning algorithm goes with procedural knowledge. Something else called economic attention allocation that governs the spread of those short and long-term importance values, which Joel also had a big head in. all these things have to work together with each other in a way that will cause each other to work better rather than step on each other's toes. And this is a complicated thing to make all these different algorithms cooperate with each other. On the perception side, also you have a sort of interaction that's needed. You have a hierarchical temporal memory type architecture, sort of similar to Jeff Hawkins' Numenta architecture, where you have different layers in the network, and each layer recognizes patterns in the stuff on the previous layer. So it's sort of a hierarchy of perception representing the structure of the physical world. But that then needs to connect with the network of concepts in the atom space. And this is something some guys are working on in Xiamen University in China, not too far from here. So one of the things we're doing with the OpenCog system here in Hong Kong at PolyU, at the MLab, is using OpenCog to control video game characters. And Zhenhua, who's the next speaker, will show some examples of that in his talk. The AI is controlling a funny little robot that moves around in a Minecraft-like way and tries to achieve various goals. This is a 2-year project co-sponsored by Hong Kong ITF, Innovation Technology Fund, along with one of my companies, Novamente LLC. And basically, we're in the long tradition of many AI projects working with blocks worlds, and we're trying to get the AI to learn to build stuff with blocks in a way that will help it achieve its goals. Like, it's a little robot, it needs to get electric batteries to keep its power going. It needs to stop big bad robots from beating it on the head and so forth. And it's sort of a playground to experiment with integrating all these different cognitive processes together. Some of the things we've learned so far, as Zhenhua will talk about, we've used a model of emotion and motivation called PSI, which came from some German psychologists, Dietrich Dorner and Joseph Bach, and that has worked fairly well. It's a neurally and cognitively inspired model of emotion and motivation, which we've used to cause the agent to try to achieve its goals in its world. PLN, the probabilistic logic network system, can be used to formulate plans to help the system achieve its goals. We've done some work with data mining the atom space of nodes and links to find frequent or surprising patterns, which has proved feasible in this context. And one thing we're working on now is recognizing coherent events. I mean, a lot of stuff happens in the world. How do you recognize a coherent event, like say this conference, or the act of going to a restaurant to eat, or the act of cooking something, the act of building a tower? So this recognition of coherent events needs to use PLN, it needs to use frequent subgraph mining and a bunch of other things. So these are examples of the kind of things you get by playing in a virtual world. I mean, the virtual world is very simple, but yet you have language, you have social interaction, you have reasoning, you have movement, you have perception. You have all the things that a mind needs to do wrapped up in a very simple environment. I don't think we can get all the way to a human level thinking machine by playing in a virtual world, but I think we can learn a lot about how to make all the complex parts of our AI system work together. The next step beyond the virtual world is going to be to use the AI to control a robot, and this is very simple footage taken from our lab in Xiamen University in China a couple years ago. We used OpenCog to control a now robot doing some very simple stuff. We didn't get all that far with it, to be honest, and we're looking to reinitiate the robotics work next year. But I think ultimately we probably do need the rich perceptual data and the rich motoric affordances that you get from robotics. But we still have a lot to learn from playing with the virtual world as well. So I'm out of time. I'll just take one more minute to go over some of the long-term vision that we have. So drawing a little robot in the video game world, there's a lot of challenges there, because getting any complex software to actually work is challenging. And we've just barely gotten to the point of having to learn to build stuff with blocks, like last week, which Zhenhua will talk about. And fortunately, we have some funding to keep going more and make it smarter and smarter. Integration with vision and robot control is also hard, and we're slowly working on that, but we're making progress. I would say, in terms of Piaget's stages of development, the infantile stage, making sense of and achieving simple goals and sensory motor reality, I would say we're still there, basically. We've got at best a virtual baby, not even a robot baby. But we have a very concrete and well fleshed out design. I think we know how to ascend the Piagetan ladder and go further and further. You look at the Piagetan concrete stage, where the system has a richer variety of learned representations and can really start to model and understand itself. And I think we can get there in the virtual world. The system is socially interacting, it's physically interacting, and it has to learn to combine perception, action, socialization, and language. I think we can get the system with a modest level of self-understanding in the virtual world, enhance that with stuff we get from the robot. Then once you get there, I think going to the more advanced levels in the Piagetan stages of development should be easier, because computers have a sort of leg up on people where formal reasoning is concerned. I mean, they can do precise manipulations and precise logic. So I think the big hurdle we need to overcome is getting the AI to understand itself, to model itself, understand what it is and what it's doing in the world. And I'm optimistic we can get there in the next few years. So if everything goes well, if we keep getting funding coming into the project, and if our ideas don't prove to be completely idiotic, if our basic plan proves correct, as I think, this is a sort of timeline that we may be able to follow. And of course, I'm well aware, like Microsoft can even predict how long it will take to release the next version of Word, right? They have a lot of money, and there's no real research involved there, so predicting the outcome of a complex software project is just not really possible, but having said that, you have to try anyway. So this is our attempt to extrapolate how OpenCog development might go if our ideas are right, and if we keep getting a modest amount of funding into the project. It could be accelerated if someone really rich gives us a lot of money. So if there's any billionaires in this audience, you can talk to us afterwards.
Yeah, that's my line.
What's that?
That's my line.
Right. So what we're working on now is what I call a proto-AGI virtual agent in the virtual world, which Jim will talk about in a moment. And what I hope is in a couple of years after that, we can get an integrated proto-AGI mind. What I mean by that is, the thing we're doing in the virtual world now doesn't actually have all those boxes and lines in our big scary architecture diagram. It has just some of them that are really needed for the virtual world interaction. What I would hope is by 2013, 2014, we could get it all in there, have at least something reasonable in every box in the OpenCog architecture, doing something in the virtual world, and maybe a robot as well. A couple years after that, more advanced learning and reasoning, which wouldn't involve any new components to the architecture, but just making them work better and be smarter. And then we get into the domain of speculation. But when I talked yesterday, I talked about biology. My work applying machine learning to analyze genetic data and brain imaging data and so forth. That's one kind of thing you can do. Once you have a proto-AGI system that can learn and reason generally, controlling simple robots and video game characters, the common sense understanding inside that system can then be deployed for all sorts of practical applications. So I think once you get a system with basic common sense knowledge working, you can then use that to make an artificial biologist. You can use it to make a service robot that will clean your house, or a chauffeur to drive you to work. And you can branch out into all sorts of different applications, which is, I think about as a sort of AGI expert. It's not yet a full-on human-level mind that can do everything you or I can do and more. But it's better than a narrow AI system, because it will have some real common sense reasoning to it. And then by putting together these various AGI experts in the common OpenCog architecture, leveraging the common sense knowledge we got from these simple virtual world and robot experiments, then you get sort of full-on human-level AGI. Then you get into what Jan was saying is so scary, of a system that can potentially reprogram its own AI code and make itself smarter and smarter and we need to think very carefully about what its goals are, how it's interacting with us and modeling us to be sure that it's proceeding in a reasonably ethical and beneficial way. No, I don't think we're going to see what some people call a hard takeoff. Like, okay, today our AI is building little blocks in the virtual world and analyzing genetic data. We wake up tomorrow morning, oh my God, the AI has achieved an IQ of 10 billion, right? Overnight it ascended from playing with blocks to ruling the world. But that's extremely unlikely to happen. The way it's going to happen is more like this. We'll build an AGI system that can control robots and video game characters, do simple stuff. We'll leverage it for practical applications like service robots and bioinformatics data analysis. One of the things you can teach the AGI to do is to program. And that's not going to be easy for it, just like it's not easy for a person to learn to program. But you can teach the AI to program. It'll start programming hello world and sorting algorithms. Eventually you can teach it to program AI. And then after that, after a bunch of education and interaction, it will learn to improve its own source code. And then you do have the whole recursive self-modification process that many others have described. And then you have serious ethical questions of how much you know about what this thing is going to do after it has modified its code in a way that you can't possibly understand. How is that AI interacting with human beings and with the other technology around it? Which are very deep and difficult questions. And I tend to agree with Joel that an open methodology in which more and more of the world is involved with this process as it unfolds is going to be good. But I also feel like we don't understand that stage very well yet, and we can't understand that stage very well yet. I think that once we get to the stages I've called advanced learning and reasoning, AGI experts, like once we have AGI systems that have selves, and understand who they are, they're doing practical stuff in the world, at that point, we're going to be able to develop more of a science of AGI. We're going to understand what we're doing, and the whole notion of AGI ethics is going to be more meaningful and less of a science fictional notion. And this is where I'm not sure I see eye to eye with Jan, although we've never talked about it in great detail. I've talked with more of the Singularity Institute people who he also knows. Some people have the idea we need to figure out a theory of how to make AGIs be ethical and be good and not destroy the world before we build anything. And I think that's impossible. I think the theory is going to come hand in hand with the practice. As we build AGI systems and have them do stuff, we're going to understand what AGI really is. The theory of how a mind works and the theory of how a mind can be ethical will emerge along with the process of actually building AGI. I think it's just a fantasy that you can make a theory of ethical AGI before you've learned to build one. And I don't think you can learn to build one by theory alone. I like doing theory more than engineering. So if I thought we'd do it just by theory, I would be doing that. All right, I've overstepped my time, but since I'm the conference organizer, I can I can go in the other room and beat myself up afterwards. So, yeah, if you have more questions about this, feel free to email me. This is a big project. It's a short talk, can't really do it justice. But we will hear a little more about what we're doing in the project right now with our next speaker, who's Jemois Shai, or however you pronounce his name.